This is a section you definitely need to read, and there's not much MATLAB you can do because the idea is we're trying to figure out how to determine the standard matrix of a linear transformation. And so the key ideas in the chapter, like they say, is learning how to verify that a transformation is linear or prove that it's not. And there are a couple of important theorems that they cover. For example, we should be, if it's a linear transformation, we should be able to do the scalar product and then do the transformation, or we should be able to do the transformation first and then the scalar product and get the same thing. The same will also be true for addition. I can either transform both vectors u and v and then add them over in the codomain, or I should be able to add the images and then transform them and I'll get the same thing either way. That's what it means to be a linear transformation. And then we have some facts that we know. We know that the zero vector gets mapped to the zero vector in every linear transformation. So if the zero vector isn't in the range, it's not a linear transformation. And because of the previous thing, that the transformation preserves scalar products and addition, then we can take the transformation of a linear combination and get the same thing as if we took the transformation of each individual vector and then scaled that transformation of those images by the scalars C1 and C2. We'll get the same thing as if we just did the linear combination over in the domain and transformed that. They also make it very clear what we mean by the standard basis vectors or the standard coordinate vectors. So we always use E1, E2, and these are vectors, right? Up through En. And they do make the point that sometimes we mean that different things using the same notation. They're saying that this could be E1 if I'm in R2, right? That's E1 for R2, but this is E1 in R3. So E1, we just use these to refer to the columns of the identity matrix. And then we have to know what dimension we're talking about it. Usually it's clear what dimension we're talking about, and so we don't specify it. And then here's the heart of the chapter. Here's what they're saying. Look at this, right? That if I think about these vectors, right, multiplying by the standard basis vector just peels off a column, right? So multiplying by the first standard basis vector just peels off column 1. The answer is column 1. And when I multiply by the second standard basis vector, it peels off column 2, right? This is grabbing this, and the same thing. This is going to be right here when I multiply by the third standard basis vector. Why is that important? Well, it's important because whatever happens to the standard basis vectors under the transformation determines the standard matrix, right? So if I have this transformation and I transform the first basis vector, that's the first column of the matrix A that does the transformation. And if I take the transformation T and I transform the second basis vector, then that transformation is the second column of A, the matrix that does the transformation. So we can use this in the reverse as well. So it means that if I know where the E1 vector gets mapped, I know the first column of A. If I know where the last vector, last basis vector gets mapped, I know the last column of A. So this is how you find the matrix of a linear transformation. You determine where each basis vector gets mapped to. If you can figure that out, you know the matrix.